If I want to know how molecules stick together, the intermolecular forces, usually it's because a positive and a negative on two different molecules are sticking together. But how does that work if the molecules are nonpolar and they don't start off with a positive or a negative charge? We'll find out what these London forces are. Let's jump right in. Now let's take a look at the weakest of the intermolecular forces, London forces. Now these are very weak because they're in nonpolar molecules. So there's not a positive side and a negative side overall for that molecule. And the simplest nonpolar molecule I can think of is hydrogen gas, dihydrogen. So there's two electrons. Let me just draw those two electrons in this molecule, put a couple of dots in there, and they're floating around, zipping around this electron cloud of two electrons. But because they pull equally on that bond, there's not one side that's more positive and there's not one side that's more negative. They're equal. So if the stickiness, the intermolecular forces, comes from positive sticking and negatives, I need to somehow make a positive and a negative. So here's what we think happens in these London forces. If I have two electrons in there, and let's say at any brief moment I take a snapshot. Freeze! Where are you, electrons? If they're right there in the middle, there's not a they're kind of equally negative on both sides. There's not really a dipole moment. There's not a positive and a negative side. But if they're sloshing around a little bit and they both end up on one side of the molecule when I say freeze, just for a very brief moment, if they're both more on one side than the other, there's kind of a negative side to the molecule and there's kind of a positive side. Now, in just a moment later, they'll slosh back and I lose it. But for that brief moment, just briefly, you get a positive and a negative spot. Now, if there's another molecule with two electrons in it for another hydrogen molecule, in this case, when there's just briefly a positive side, well, the negative electrons in this molecule, what happens to those? Well, opposites attract. So those negative electrons will be attracted towards that positive. And for a brief moment, I have a negative side and a positive side for that dihydrogen molecule. So we'll get a little stickiness between these two molecules, and intermolecular force is pretty weak because it disappears a moment later when the electrons slosh back and it becomes nonpolar again. But for a brief moment, they stuck together. Now, what happens if I have a molecule with more electrons in it? Maybe now, instead of like hydrogen, maybe I'm talking about bromine. Two bromine atoms, nonpolar molecule, but what if there's a whole bunch of electrons now in bromine because it's much farther down on the periodic table? A lot more electrons in those two bromines. And if I take a snapshot, it might be nonpolar. But what happens if the electrons start sloshing around a little bit? Now, much like when my kids were little and they would get into the bathtub and I'd fill it up with water and they'd start sloshing the water. If they sloshed the water back and forth, they would move, back and forth they would move, and because it was fun to make the water splash up on one side and then on the other side. And then when they got a little older, I noticed that if I had too much water in the bathtub, and they get to slosh in it, especially when they were young boys, they could splash the water out of one side and splash the water out of the other, and they could really get a whole bunch on one side and then a whole bunch on the other if it was full of water. So I need to lower the amount of water so they couldn't splash it out of the bathtub. That's sort of what's happening here. If I have a little bit of water in my bathtub, like in dihydrogen, if it's just two electrons, they don't slosh all that much, those electrons. But if I have a lot of water in the bathtub, or a lot of electrons in my molecule, they can slosh a lot more to one side or the other. And I could, if I say freeze, and they've sloshed a lot more to one side than the other, just for a brief moment, I can get a very negative spot and a very positive spot. And if I have a lot of electrons in the other bromine molecule, well, as soon as I make that positive, a bunch more will be attracted over to one side. to make it very negative and very positive. And that negative and positive spot will stick together and with a London force. Now, normally it's fairly weak, but if there's enough water and enough electrons sloshing around, I can go from a gas, which is what hydrogen is, to a liquid for bromine. Bromine's a brown liquid, and that's because we think there's more electrons that can slosh around. There's no polarity normally. It's a nonpolar molecule, so you won't get dipole-dipole interactions. There's no hydrogens in it, so you can't get hydrogen bonding, the strongest kind. So all we can really think of is, because it's nonpolar, this induced dipole moment that you get whenever they slosh over, and it induces the other molecule to make a dipole moment. When you induce that dipole moment, they start to stick together. What if I make it even more electrons, go down further on the periodic table to 2 iodines, diiodine? Well, if I have even more electrons, the water can slosh even more. You get even more negative spots, very positive spot. These electrons, you get a whole bunch of them that would slosh over to one side. You get a very negative spot, a very positive spot. You get a very strong interaction between those, very sticky. That's going to be even more. So even though it's a London force, these nonpolar molecules, it can stick together enough that this ends up being a solid. Iodine is a kind of a purplish solid. So London forces come into play when you have nonpolar compounds, and you find that the more electrons you have, the more they'll start to stick together. So in organic chemistry, you'll find this if you have a nonpolar molecule like CH4. It won't stick together with another CH4 very well. It's more like the hydrogen kind of situation. But if I get a molecule with a whole bunch of things on it, well, that's terrible, 5 bonds. But if I get a molecule, let me just draw carbons, with a whole bunch of carbons on it, it's more likely to start to stick together more and become a liquid. And if I get a whole bunch of them together, maybe it can even become a solid. So nonpolar hydrocarbons like this can start to stick together through London forces. One more thing I want to point out. If I have two, let's pick 2 compounds. One looks like this, 1, 2, 3, 4, 5 carbons. And the other one looks like this with 5 carbons. They're both nonpolar molecules, shouldn't stick together all that much. But which one, a bowl full of these, a beaker full of these rounded ones, or a beaker full of these skinny, long, noodle-like ones, which ones tend to stick together more? And the London force argument for this would be spheres like this, these branch compounds, have less surface area, so they end up having less London forces and they don't stick together as much. And these longer, skinnier ones have more surface area, so they end up sticking together more. So this would be more liquid-like and more gas-like. Higher boiling point, lower boiling point. I like to think about these long noodle-like ones. The way I remember this easier is I like to think about the spaghetti noodle effect. If I have cooked spaghetti, these molecules can start to intertwine with each other, and they can't fly away as easy whenever I try to heat it up. So the spaghetti noodles, they clump together a little bit more. They get intertwined. You have to heat it up more to make them fly away. They would have a higher boiling point. Compared to more ravioli kinds of noodles, cooked noodles, those are easier to pull out of the pot. So I hope the spaghetti noodle effect maybe is helpful. So those are the weakest forces, London forces, for nonpolar molecules, even though they can still be pretty strong if you have enough electrons in them. I hope that was helpful. Hey, like and subscribe to the channel so I can continue to help you in your organic chemistry journey.